seminar of the year. It's my pleasure to introduce Dražen. He's going to be talking about affine vertex algebras, collapsing levels, and representation theory. Feel free to start when you're ready.
Okay, thank you very much. Thank you very much, Flor, for invitation. So it's my pleasure to present talk at your seminar. This is very good idea, and I briefly looked at the abstract and other talks, and it's very fascinating. So it seems that all new results were already presented here. So there is probably no space for me to say something new since a lot of things are really solved. So it seems that 2020 is a great year for VOA people and for all community. So but this is also so. I'm very sorry that we are not able to travel, no? But this online talks, this is probably very good solution. So, but about subjects. So last month I had one talk in Europe, and I was surprised that and wanted to present some new results. But it seems that people in the audience were very much interested in slightly older results. So essentially, I prepare something new, but then I need to recall my knowledge about 10 years ago about the status. So it seems that there are plenty of new results in the area, and still we have some old problems which deserves full attention to the theory, and it's a good idea. It's a good idea maybe to see some recapitulation, what is still open, and which problem we should be focused. So I put very general title, but of course it should be more specialized. So we still have this project, so you are all welcome to come. So we are essentially not spending any money. I hope they will leave us. So in the case that you want to come, we will always find you some hotel and organize some talk. So about the topic. So I somehow wanted to speak about something which happened in last 5 years. In last 5 years, and as I mentioned, it's very difficult to see what is really happening. So in blue are topics which I want to say a few words, not much about it, but few words only. So in black I will leave without maybe some other people can speak about this, but essentially, even in this topic in blue, I will not cover much. So I put this collapsing level. So collapsing level, it seems to be very interesting subject, and a very interesting subject, and related with many things. Essentially, this talk will be mostly related to my point of view, which can be wrong. Which can be wrong, but or people can think in different way. But I will somehow want to say what is my opinion about this subject. So collapsing level and this application. So there's a lot of new. I realized after I put the title that there are a lot of. That Ed Moreau also had talked, but my talk will be completely different on different subjects. Essentially, I'm concentrating on relatively older stuff. Logarithmic vertex algebra, old and new. So what are old VOAs? So all you know for that, they are like triplet VOA or something. This is something which almost 20 years old, and still these logarithmic VOA are certain inspiration for many other stuff and many other ideas. It seems to me also that things are maybe more clear. And then this explicit realization of affine VOA and W algebra, I don't want to speak a lot of things about this, but it seems to be that this is nice tool. This is nice tool, and maybe in last 5 years I was concentrated on some subject related to affine story. Conformal embedding and affine vertex algebra, I already had a lot of discussion with all of you and the other guys in the area. So it seems that still there are a lot of problems, especially for getting conformal embeddings in W algebra for non-minimal nilpotent. So I think this is and get decomposition. It's still there are a lot of decomposition open, and for this one can use various kind of methods like you use tensor category. This is one method. So the second method is combination of something which should be related to this explicit realization. The Whittaker module stuff essentially is also very important. Somehow they are on the door that they should be included in some consideration in the category. And fusion rules, of course, are related to everything. And so these subjects are somehow it's happened to be in focus in the last 5 years for me, but of course there are so many other stuff. Many other stuff, and just see what is happening about this collapsing level. And in the collapsing cases, the definition is that the level case called collapsing if we take minimal W, if we take any affine W algebra and it collapses to affine part, and then level is called collapsing. And in a joint work with Katz, Mossen, Ederfreire, Papi, and Perchet, we classify collapsing level in the case of minimal nilpotent. So we mostly use lambda bracket formula. We use lambda bracket formula for getting lambda bracket explicit OPEs to get some condition that generators of this W algebra vanish in the simple quotient. So essentially it was very simple. It was very simple idea, but it requires some work to write down explicit formula. And recently there are more work about the algebra. So Anne Moreau, he presented many talks in recently few years. I remember her talk in Split, then in Zagreb, then in Split, but then Dubrovnik. But I also noticed a very interesting talk at your seminar about what's happening in other nilpotent cases. So it's about it's about current state of. In my opinion, maybe somebody has much newer information. So, but what are for us interesting? So in our paper published in 2018, we prove semi-simplicity of certain categories of module beyond admissible levels. So essentially. We show that that this concept is useful for describing some representation theory beyond admissible level. So at admissible level, we have nice character formula. One can use character formula, a lot of other stuff for studying. But beyond admissible level, it's not so clear what are characters, what is maximal submodule in universal affine algebra. So how one can do the representation theory. So in this case, one needs to find some other approaches, and probably this was just one possible part. So we use this W algebra to get semi-simplicity of representation, and then so this was our goal, and I will discuss it a little later. And Thomas and Ginway then showed the existence of vertex and tensor categories on such level. So this is one application, one possible application. What is happening? So somehow it's much better if you have semi-simple category. Probably one can do tensor category job for non-semi-simple category, but when it's semi-simple, it's like you have some category which behave like rational or something like that, and one can show a lot of things. Okay, if there is okay. Just let me just first say a few comments. So let's say that KLK be the category of ordinary module. So this is like category of ordinary module for affine algebra. So we irreducible mode, simple quotient in this category are simple object in the category are modules which on the top has finite dimensional module for G. Let us consider here only the algebra case. Let us although the super algebra is maybe even more interesting, but let's consider here briefly what is happening. So consider this category for the algebra and questioning when this category is semi-simple. Simple question when this category is semi-simple. And what is known, what is definitely known for a long time, that when K is positive integer, then this category is semi-simple because it's rational. So then LK of G is rational. So this is the only case when we have rational C2 cofinite. When K is not rational, when K is not rational number, then so for generic cases, Kazha-Lushik theory implies the semi-simplicity of the category. One of their results is semi-simplicity of the category of Kazha-Lushik category. And when K is admissible, then Arakawa proves semi-simplicity of the theory. So problem was study semi-simplicity of KLK for K non-admissible. And we proved in the paper for 2018 that KLK is semi-simple in the following cases. When K is collapsing, so collapsing level, which I mentioned, this probably holds also for Lie superalgebra case. When W algebra is rational, and then what is also when VK G of F theta is semi-simple in suitable category of modules. I don't want to be very precise. For example, when we get Heisenberg, we have take level 1 representation of SLN, then it collapses to level -1 level -1 representation for affine. It collapses to Heisenberg, and we know that Heisenberg vertex algebra is semi-simple in the category of ordinary modules. So there are infinitely many modules, but in the case of ordinary non-logarithmic weight. So essentially we use this semi-simplicity. So what is probably this is somehow one need to look maybe more carefully. But when we get rationality or collapsing level, it's automatically it's automatically we get semi-simplicity. So we prove this. So let me say one thing about this proof. So what is situation? What is connection with other proofs? So in the case of admissible, in the admissible case, one needed to classify all irreducible representation in highest weight category. And then after classification of all irreducible representation, we get semi-simplicity for free, because there is cache done for criterion or something like this, which follows from description of admissible representation. But here we cannot get this for free. So one need to do some extra work about the representation theory, and it's very interesting that it is very difficult to prove. I don't know any proof beyond admissible level which is purely Lie theoretic. So if we use Lie theoretic methods or orbit of the Weil group or something like this, some playing game in category O, there is some problem. So, but vertex algebra somehow control the situation, and one can see in our paper what exactly happened. But still, I think it's still good maybe to have independent proof of this. I think it's one possible way to get some different proof, because I really don't know, for example, level -1 SLN, how to prove semi-simplicity without this W algebra approach. Without this W algebra and collapsing level approach, how one can prove directly. But still I think this is very good. This is very good problem, which can now holds more. Maybe we can try to extend this in certain sense. Somehow it's nice, as I mentioned, it's nice to use this W algebra approach, but still probably one can try to use this highest weight representation theory, because W algebra is in some cases are very complicated. It can be very complicated. But okay. And what is also for me interesting without complete explanation, so we have what is with K of K. This is essentially now in the book. So if we take, for example, SL2 level -4, level -5, if we have integer level below the critical level, then the category K of K is not semi-simple. But still, one can have tensor product and tensor category approach, but it is not semi-simple. This is not semi-simple. But what is interesting, but some modules can be completely reducible. And essentially we detect this in the theory of conformal embeddings. So in the theory of conformal embeddings, for example, let us consider one case. So take beta gamma vertex algebra, and take third power of beta gamma or well vertex algebra or symplectic boson, how you want. And then there is conformal embeddings of -3/2 SL2 times. Also, Andy Lynch also studied this example using his work. So we consider this conformal embedding, and you see -4, -3/2 SL2. We know now that they're semi-simple category. So we automatically know that everything from the KLK is completely reducible, but -4 is not. We still have some nice VOA, which such that in the decomposition involving -4 SL2, we don't get completely a reducible representation with very explicit formula. But here in this, take 3 copies of beta gamma. 3 copies we get conformal we have conformal bearing. Of course, this algebra is automatically simple inside, but we also prove complete irreducibility. And our proof somehow uses character. For -4 SL4, it was somehow not complicated to calculate characters and see what is happening and then using this character formula, we get complete reducibility. And we needed, this is also interesting for Shoshank, that we need some combinatorial identity. We use some, but non-combinatorial identity. Combinatorial identity in using, and as a consequence of this combinatorial identity, we get this semi-simplicity. But problem is how to get this in different way, how to use some kind of tricks, other maybe unitarity or maybe some other stuff to get this completely reducible. There's some other example in our paper for which we still don't know how to prove completely reducibility, but it seems that they are completely reducible. So question is why, but so this is find some more conceptual reason why, because we are involved below the cut. So we use vertex algebra which are not for which KLK is not semi-simple and get semi-simple. So this is very very interesting, very interesting. And let us go back. So another stuff. So as I mentioned, I now some. So I finished with this collapsing stuff. And what logarithmic? I mentioned logarithmic old and new, but not all new, not all new. So I would just say old VOA and some easy new. There are some high rank triplet which I don't want study. I noticed Sugimoto had nice talk about this high rank triplet. So about triplets. So we have triplet algebra associated to 1P models for the Virasoro algebra. So which we started somewhere almost 15 years ago with Anton, and then it was a relatively new stuff for mathematician, but also still known for physicists working in this direction, like Gabriel, Kaush, Semikhatov. Also, he had nice Fagin, Semikhatov, Tipun, and a lot of things, and a lot of they published a lot of interesting paper. But then Floor, Carcanville, but essentially, so the triplet are C2 cofinite and non-rational represented proof in the paper. Decompose, and what was interesting, we decompose triplet SSL 2 times Virasoro module. So, and then we get this decomposition. And later we prove that this automorphism group of the triplet is PSL2C. In PSL2, this essentially, this decomposition is still, I think this is not completely satisfactory, because this action of the SL2 are nice in the case of symplectic fermions. We really have nice action, but for P greater or equal to 3, it will be still useful to have more explicit formula. Even for symplectic fermion, one can see that some part of this SL2 action is not completely local. So we have E element of the SL2, which is essentially one screening operator. We don't have problem with Cartan, but with F. And if you want to get explicit formula for F, it turns to be, even for symplectic formula, symplectic fermions is not local. So this is triplet vertex algebra. Then we have doublet. Doublet is a simple current extension of the triplet, and we have in decomposition we get decomposition like this. Then we have singlets. So the old VOAs are, I can say, triplet, doublet, and singlet. Technically, singlet is the doublet is abelian intertwining operator. It's more for P even. This is vertex superalgebra. For P odd, it's just abelian intertwining algebra or generalized vertex algebra. It depends on the terminology. But singlet is very nice, and essentially I started to study singlet before, and it turns out that in order to prove a lot of things about triplet, one need to understand very much singlet algebra. So there are a lot of new achievements in this story, but this is so they're all new. And you see, in all cases we have this SL2 action with SL2x by the derivation. And how to get new vertex algebra? Get new logarithmic from old logarithmic vertex algebra. So this is one section. Maybe I hope I won't say anything wrong here. But so we want to construct some new log VOA having similar properties as old VOAs. From old we get new. We get new, and so we expect. Let us put some expectation, so that this V new will behave similarly like triplet or singlet or doublet. So we expect that we will have SL2 action, commuting with the action of some other VOAs, some W. And for this W, we expect that W are model for some still unknown W0, having SL2 fusion rules. Let us expect. And as I understand, there are two different methods. And people using this vertex, Larkin, Thomas, Shoshank, and McRae, probably other. So they use, I put R. It's good for McRae. It should be M, CKM. But I don't know. So it can be good for, so C means, C is, only C is Thomas K, Shoshank, and with R we have, but it means that what M, that should be M. But so they use gluing method. So they using gluing method. So this is part where I will be probably wrong. So essentially, if I understand, so we need to know this W algebra, this algebra W0 very much, and we know a priori the vertex tensor category and fusion rules, and then you glue somehow. So this is one you maybe didn't use for this case, but some other. So essentially, this is the method which I don't know much, but this is one possible method. So one first understand W0 and fusion for W0, and use this tensor category on W0 to get this new VOA, and this is where it's tested in some situation. But it seems to be so we need to know vertex tensor category before, and as a consequence we get new VOA. But other possible method is, but essentially I started these topics in some cases before, and trying to solve something very more elementary, maybe more elementary. So this is one other possibility, to get vertex operator algebra directly, explicitly directly, using free fields and some other methods. And this it seems that they will have consequences for fusion rules and this business. So that either we can use directly, or we can get something a priori. So this is like philosophically what one means. So essentially, I constructed some of this new, and then it seems that for full understanding, one needs to have some combination of such approaches. So let me study this new. So what we essentially have, let us recall that SB1, this is Weyl vertex algebra of beta gamma or symplectic boson. Somehow, I don't know, cats call this symplectic boson. So we usually and essentially we use Weyl vertex algebra. I don't know, because we studied this Weyl algebra for study level -1 as symplectic in some cases. So we take this symplectic boson, and then we need one lattice vertex algebra, FP1. So this P over 2, it's sometimes again lattice algebra, it sometimes is generalized lattice algebra or abelian interfering algebra, but doesn't matter. So this is lattice vertex, and this P can be also positive or negative. It can be positive or negative. And there is one famous algebra, one of the most famous logarithmic algebra. This is BP algebra, which introduced by Kreuziger, Rideau, and Wood, and this BP algebra are obtained using, just take this doublet stuff. This doublet algebra and tensor, and we tensor this doublet algebra with this lattice stuff and take Q1 orbifold. And then this is definition of BP algebra in their paper. So this is BP, and next algebra is not so famous. This is VP algebra. VP algebra. So this VP algebra. So this VP is somehow directly connected with the triplet doublet 1P models. But VP algebra. So I got this VP algebra somehow when I wanted to get explicit realization of level -3/2 SL3 simple affine Lie algebra. So this was my tool. So I investigated. I wanted to give as many explicit realization I can have, and in order to get this explicit realization, somehow I investigated this Wakimoto module. So Wakimoto module, Wakimoto bosonization gives you homomorphism from affine in the case k plus 2 over 1p to tensor product of symplectic boson with the Heisenberg. This is Wakimoto module. And then this Heisenberg involved here is extended to this lattice stuff, and we get this Wakimoto type of module. But then we use one screening operator for this homomorphism and just take kernel of the screening operator, and we get VP algebra. Motivated example are this n equals 4 superconformal algebra with central charge -9, which also appeared in some work in physics recently also. So and in this case, when this n equals 4, we get something more simpler because then we take p equals to 2, and this is just BC system. So then we have this BC system. Now this is definition of VP algebra, but in the paper I just essentially consider this case p equals to 2 and just have discussion. and just have one section about this, and then during some lot of conferences I discussed with Thomas about this VP. I was very happy that he was also very interested in his VP. RP is obtained from VP in the same way as BP is obtained from doublet algebra. So this is some kind of realization, but only as you see here, this somehow we have this triplet kind of realization of this VP, but it seems that it is important to have action of the SL2 action like in the triplet, doublet, and MP case. And we discussed it during my visit last year. So it seems that one can use some inverse of Hamilton, some kind of inverse of Hamiltonian reduction to construct directly VP from AP. And this is done by using some half lattice, very important half lattice VOA, which is obtained, take rank 2 lattice, ZC plus ZD. So this is some hyperbolic lattice. It should be one here. And consider lattice VOA. This is how lattice VOA will be if we included all lattice, but we'll just include half lattice, and we get something smaller, and then we can take P0 1 half, and this P0 1 half will be just a simple caret extension of this pi zero, and what's happening, I use interpretation without screening operators, we get that this VP is obtained as a tensor product of pi 0 1 half of doublet with pi 0 1 half, and now doublet times pi 0 1 half. This essentially this doublet is infinite direct sum of the Virasoro. Tensor with pi 0, we automatically go to SL2 story. SL2 story, and then we take maximal integrable part of this SL2 action. And this is also interesting. This works for P equals to 1. For P equals to 1 also. This works. We can V1 algebra also. It's just not, so this is also important here. And then we use this SL2 action of this AP algebra of doublet obtained here, there is here, to get SL2 action on VP. Somehow this SL2 action is well defined of this maximal integrable part. This can be also described as a kernel of certain screening operator. And then get this decomposition. This is completely similar like in the case of doublet, and similar for triplet. And there are some consequences to tensor category, which is what was also nice that we can have isomorphism of abelian intertwining algebra. We can define Drinfeld-Sokolov reduction of VP and get AP, and of RP get BP. So somehow RP. This gives maybe better understanding of this some new logarithmic algebra as one first step in generalization to see the just inverse of AP and BP algebra. And what is next? What is next step? Next step in the story. So we wanted to get new stuff like this. Question is, can we get something new? Essentially, we expect that one can use every put here every VOA with SL2 fusion. And as I mentioned, I want to use last approach. explicit. We want to use last approach, but of course, second approach is also welcome. So do we have more VOA with SL2 fusion rules? With SL2 fusions, like in the category of KLK. Of course, there something happening in something happening for below the critical level, k equals to -3. It's exactly interesting that in this case k equals to -3, it's mapped to central charge 25, which are investigated by Florencia in his talk. But in affine case, essentially, so we have k equals to -3, then k equals to -4. It also have SL2 fusion. Essentially, it's still not completely proved, but we don't need complete proof because we will have complete explicit realization. And then, for example, -4 SL. So minus, nice example is take SL2M level -m, and then we have module with expectation of SL2 fusion rules, and which are good candidate to building new VOAs, and especially this guy at -4 SL2, but in order to get SL2 fusion, we need to multiply the weight by 2. We multiply weight, and then we get SL2 fusion. And then what we get, so from AP we get VP. From VP we get some other VOA, but applying such strategy, we can reconstruct one very famous VOA. This is level -2 SOA. So one can consider algebra which is constructed from V1. We call Z1, and then to get, and explicitly we can prove that such algebra can be constructed, and then in this way we can reconstruct this level -2 SOA. So this is one possible algebra. So somehow generalization of RP algebra. Next generalization we get some nice algebra like this D4 level -2, but one can expect much more example in this way. So okay, let me now say about some other things. So as I mentioned here, I want to say something about explicit realization. So this third and fourth bullet, and I will speak in the framework of one recent work with Kazuya and David. So let me just recall definition of, which you all know, WSL3 principal algebra, also called homological algebra. So the homological vertex algebra, ZK. So this is the principal W algebra of SL3. So this is universal vertex algebra generated by the fields T and W, where T is a Virasoro, and W is singular vectors with conformal weight 3, and W times W is the following lambda bracket or OP. So this is very complicated, but very known. And formula, we have formula for central charge and certain normalization. So just I want to say one part of the story, how one can understand this relaxed high weight module, which are also it is also very popular, and a lot of approaches to this. In the case of Breshatsky, sorry. So I first said zamological, but in the case of Breshatsky-Polyakov algebra. So for Breshatsky-Polyakov algebra, Breshatsky-Polyakov algebra is the universal vertex algebra having 4 fields, L, J, G plus G minus. All of them are even, and they satisfy the following lambda bracket. So this is the simplest minimal affine W algebra. And notice here we change here a little bit Virasoro to get the G plus is of conformal weight 1 and G minus is of conformal weight 2. I forgot that. I hope that I haven't missed some derivation the formula. So this is Breshatsky-Polyakov, and essentially and this is zamological algebra. And the question is what is easier, what is more complicated? Both are them complicated, but as we discussed, in order to so in the case in our spirit, we will always want to explain more about affine algebra. So somehow and want to explain affine algebra from W algebra, but here there are no affine, but somehow Breshatsky-Polyakov is closer to affine. This is affine W algebra. So somehow we want to show what is the relation between zamological algebra and this Breshatsky-Polyakov, and it's obtained in recent preprint with Kazuya and David. So when k is not minus 3, so just forget one important thing here, that BPK upper k means universal and lower k means simple. And here also the upper k is upper index k means universal and lower k is simple. This is traditional. So we have and let me just explain that we have this minus 3 k different than minus 3, and what is more important, we can solve minus 3 also here, but what is more important, 2k plus 3 is not positive integer. 2k plus 3 is not positive integer. We will discuss later what is important. Then there is non-trivial vertex algebra homomorphism from simple Breshatsky-Polyakov at such levels. So not integer case, not half integer case, but all other is allowed. So all other cases are covered. And we can embed this BPK to zk times pi 0, the same pi 0 which we use in this in this SL2 case, where we have this here, pi 0 is defined here. The same pi 0 we can use in this for inverting a reduction from some kind of inverting and reduction from zamological to Breshatsky-Polyakov. So we can embed simple BP Breshatsky-Polyakov algebra in this tensor product, and formulas are slightly more complicated, like in the SL2 case. We have formula for G plus, for J. We have conformal embedding, essentially. We have conformal embedding of BPK algebra to tensor product of zamological with pi 0, and this T is Virasoro in zamological, and omega pi 0 is one usual singular vector, one usual relatively usual conformal vector in pi 0. So this is some kind of conformal embedding, and there is a formula for G minus, which is, as I mentioned, slightly more complicated here. So this is formula for algebra, but I want to say here why the one problem which is especially important in such kind of business, of relaxed business or a free field realization, is how to prove simplicity. How one can prove simplicity. So what is happening? So at admissible level, we somehow know the structure of this BPK or ZK, but even in SL3 case and BP case or Z case, is a logical case, put K equals to some non-generic, non-admissible levels. I don't see that solution of character formula or description of the model is completely solved. But still, we can prove simplicity of this embedding by mostly purely vertex algebraic method. So we don't use anything category or any business from the representation theory. We just like use old-fashioned vertex algebra method and direct proof of that something is simple. And let me just say how we get this. So this is in first step, we show that Bershadsky universal Bershadsky-Polyakov is embedded in tensor productive ZK type tensor pi 0. This is starting point. So we have embedding of universal, and then we pass to the quotient. So we put ZK to be quotient of simple quotient of the homological algebra, and we get composition of this embedding here. So we get representation of BPK on tensor product of simple homological W3 algebra with pi 0. So question is, when this simple, when we will get embedding of the simple algebra. This is important. If we get simple, then we can use representation theory of homological tensor with the representation theory with non-homological. So if this tilde BPK is not simple, of course, then it must contain singular vectors, subsingular, but it must contain singular vectors. And essentially, what is interesting by using some methods, we can prove that then it has the form singular vectors in, it has the form singular vector in the homological algebra, but we already took simple. So it must be one, must be vacuum with some lattice element. And then this is G plus, and then we calculating weights, conformal weights. This we show that n must be positive integer, so it's the power of G plus. So it's power of G plus. So in the case it's not simple, it must contain singular vector which is power of G plus, and one can easily check that this can happen only for integer or half integer. Only for integer and half integer, we can have, for other case, G plus n is not singular, and this can be relatively easy obtained for using OPs here. So just only G plus n are singular in this case, and this proves that BPK tilde is simple. So, and this gives simplicity. This is just want to show this part of the story. And what about relaxed? What about relaxed? So this is even more interesting. Relaxed, in order to get a relaxed module, we take some weight pi 0 modules. We get weight pi 0 module, pi minus 1 lambda, and take any possible ZK module, and we can tensor this ZK module with pi minus 1 lambda, especially let us take highest weight. We can take highest weight module for homological algebra, for W3 algebra. Highest weight are parameterized by two numbers, delta and W, and then we tensor with pi minus 1, and we get relaxed BP modules, Bershadsky-Polyakov module. And question is when it is irreducible, and using similar methods, we can prove that any incidence can be kept only on the top. on the top, so we cannot have any submodule below, and on the top we can investigate irreducibility using this cubic equation. In SL2 it was quadratic equation, but here we get cubic equation, and this Rm lambda is irreducible if and only if the polynomial pk delta w has no roots in the coset lambda plus z. So this is the nice criterion, and we now have plenty of irreducible relaxed model for arbitrary level. Even for some level for which we don't know representation theory of homological algebra, we can get High weight. If we know the character of homological, it's very easy to find character of this relaxed high weight model. So and what is the use of this relaxed? This is perfect. There are plenty of application. But before that, let us consider case which is excluded here. What is happening when 2k plus 3 is positive integer? What is happening in this case? And in this case, this case, we should divide this in this case. One thing is, in the case 2k plus 3 is positive integer if we consider simple, not universal. Simple, there are no relaxed. One can show there are no relaxed models. So we have just ordinary high weight model, just ordinary high weight model. Half integer case was solved by Arakawa, then BPK is rational. And integer level case, we studied it by former PhD student Anna Kontretz, and we have two attempts. In first paper, we haven't classified all, but recently we learned some tricks how to get complete classification. So we classify all irreducible BK modules, which are of completely different kind of type, like in the admissible case. So this integer case is really something very, very interesting, and I will show later why. So in the case when k plus 2 is the positive integer greater or equals to 1, we get that representation are an union of certain zeros of polynomials, k plus 2 polynomials. So I think it's some good new candidate for logarithmic VOA. It's something which happening very in the logarithmic behavior. Let me show in the example. For example, k equals to -1. It's collapsing. It's just Heisenberg. As I mentioned, k equals to 1 is Heisenberg. But I won't speak about level 0 case. Just say that BP0 is embedded in the tensor product of symplectic fermion with lattice with the BC system. So but interesting happen. So with no classification all, but very interesting things happen in the level 1. And the level 1 case, then we found some kind of, we learned from you guys that we call you this Kazama-Suzuki duality. Kazama-Suzuki duality. So Kazama-Suzuki duality was famous for the description of relation between SL2 affine and n equals 2. But here it can happen everywhere. It can happen in many other cases, but we found something which is not generic. This is not generic correspondence. It happens for one specific level. For this specific level, when k equals to 1, then BP1 is in this Kazama-Suzuki duality with very interesting algebra. This OSP algebra on this super linear level, -5/4. -5/4, this is, of course, admissible. admissible. But in the literature, this case was studied by Simon and David. And David and some other guys, they present some Verlinde type of conjecture for this OSP algebra. My impression is somehow that, but here we have relaxed. Still plenty of relaxed model, but then, as I mentioned, we don't have relaxed here. So just ordinary. So essentially relaxed are described by ordinary. So this is some of possible way that one can somehow from OSP transfer to BP case for this particular level. Similar type of relation apply for symplectic boson in GL1 fusion in the paper with Veronica. Similar things we studied last year. So essentially, this kind of relation is very interesting. It's very interesting, and somehow what is very challenging for me, what happened for k equals to 2 for so it's what is possible relation of BP for level 2 or greater. It should be, they should be related with some other nice VOAs. So let me, so this is one thing about this relation, about this relation for BP algebra. One can expect, I think, similar behavior of many other minimal W algebra at integral level. Minimal W algebra of maybe subregular W algebra on integral level. One can expect probably similar type of relation on some specific level. So it's not, it will be nice if it was generical, but no, BP are not related to SP generical, but just on this specific level. And as I mentioned, I wanted to say something about what is use of this huge algebra. So essentially, we discover using this BP algebra, we discover realization of some nice relaxed high-weight SL3 model having all infinite dimensional weight space. So if we tensor with this with certain guy, we get module for affine SL3, which is relaxed, but having all infinite dimensional weight spaces. This is very challenging because we don't use Verlinde formula because there are no characters. On the top, we have infinite dimensional. What is also important, somehow, this is long project, how to include Whittaker in this whole business, And what is also interesting, how one can, as I mentioned before, how one can construct new semi-simple categories. So this is related with first part of the talk, how one can construct new semi-simple categories for affine algebra, for W algebra. So essentially, the natural candidate, but we need maybe to involve some new methods in construction, and essentially I like one thing that one can use a real vertex algebra technique here, which is mostly, so we essentially in many proofs here, we just discover relation between algebra, between a lot of algebras, but essentially most of proof are directly vertex algebraic. So in such kind of free field realization, we just use some vertex algebraic tricks, some methods without using huge machinery of representation theory of Lie algebra. So this is, I think, this is not the only important how one can how that one need to prove something, and it's important how one can prove this. Because if we find some specific motivated proof of some relation like this, we can maybe understand better what is happening here and how one can extend this. Okay, thank you very much, and I wish you best for Christmas and holidays and New Year. Very productive New Year.
Thank you so much. If you have any questions for Dražen, please feel free to unmute yourself and go for it. Thank you.
I have one question.
Yes.
Thanks very much for a very interesting talk. The homomorphism from the BP algebra to Zemlyanikov algebra tensor pi 0, do you have any idea how that generalizes to higher W algebras? For example, if you replace a Zemlyanikov algebra with principal W algebra of type A, then what is a general version of that?
Yeah, but so what is essential? I prepared this for comments. So we have here this BP universal and BP simple, and then we take this W3 or ZK algebra, and one get that tensor product. In this tensor product, we get embedding of BPK. So I hope for example for what do I probably, so what is next for SL Thomas or something, so SL4, then we can take principal and maybe again tensor with some pi 0 version, but again something that we can get embedding probably of SL maybe SL4 subregular or something like this. I'm not sure, but in any case it should be relation like this, or even for some other. So this is so in this case I think one can expect much more relation like this. So I think the idea is to use SL3 principle with something with some SLN principle and this is I think obtained at a critical level. Such kind of realization I think obtained by Naoki and something at a critical level version, but at one can I think expect something like this. So just gave maybe SLN for some nilpotent, we can obtain something in this spirit. But as I mentioned, my intention was when I start. So we first started this business for SL2, as you know. So for SL2 we have this LK SL2 was including Virasoro tensor with again pi 0. And again pi 0, but here I just want to show this illustrating example of SL3 and not completely. It is not only the problem how to get as many realization as we want. Idea is I think how to show here how such kind of realization can happen, like this. So how one can prove irreducibility of relax? How one can prove study some purely representation theoretical points. So here, probably I expect here for SL4 that one can get similar kind of realization, and probably one can do for some other nilpotent. But in my opinion, this is just a realization of one part of this story of free field algebra. Okay.
Thanks.
Yeah, I just wanted to show that this example how this works.
Any other questions? Okay, if there are no more questions, let's thank Dražen again.
Thank you very much. Thank you.
Thank you. Thank you for your talk. Have a great end of the